Recording in progress.
Race. So if you're a district
Professor, we can't hear you.
or maintainer, you don't.
No.
No, sir. Can you hear me now?
Yes.
Oh, yeah. Perfect, perfect. Okay. Let me see. Let me go back. Let me go back right there. I'll share with you. There. And let me. There, perfect. And I'll bring this to our notes. This. There. Let me see. There. Copy. And send it to our notes. There.
Hide.
Is Asmongold about to say,
lecture
JD Vance watched the same Sam
1,
Hyde video that I did.
week
JD
6,
Vance knows who I am. He's not going to say that. I'm
math
reading way too hard into this.
2305, spring,
Bro, he watched Sam's video.
2025.
That's the exact vocabulary Sam
Like
Hyde
that.
used.
Okay, so
I
today
gotta go to the bathroom. I'm
is
going to kill myself.
so we have the definition of divisibility right there. A divides B means that B is equal to AK for some K in Z. Right there. And then, of course, I can write it with an existential statement. A divides B means that there exists K in Z such that B it's equal to AK, right there. So those two definitions are equivalent. Now, A does not divide B means perfect. And then, can somebody help me write that one?
There does not exist some integer k such that b equals ak.
No, that's not logical. That's not logical.
For all
For
k-
For all,
For all k in Z, B does not equal AK.
right there. Can you see that we do not negate there exists with does not exist, right there. We do not do that, right there. So every time, but thank you for making that mistake, because I would have made that mistake right there. So we still need what we studied for test 1, right there. There exists changes to a for all, the such that changes to a comma, and here we have the open sentence. Here we have the predicate. The predicate there, there becomes the negation of that predicate. Let me call this predicate PK. Here, no PK. Right there. So perfect. Okay, so now we want to concentrate a little bit here, because we have been doing a lot of examples about divisibility. So now we want to stay a little bit here. What happens when it does not divide? Right there. So what happens when I say that 3 does not divide B? Right there. So so think of some number where 3 that is not a multiple of 3. What happens when you try to divide?
You have a remainder?
Gracias. Yes, you have a remainder, and the remainder is the queen right here. Yes. So for example, 17, 3 does not divide 17. So the idea is that we still have an equation, but we are going to tag that remainder. So 17 is going to be equal to 3 times 5 plus a remainder of 2, right there. So can you see we have right there the idea of does not divide right there. So What can you tell me about the remainder? What are the conditions on the remainder right there? Of course, if the remainder is 0, you divide right there. 3 divides that number. But here, let me call it remainder. There. How many cases with remainder I'm going to have right here? On divisibility by 3, how many cases of remainder I'm going to have?
2.
2 cases. Can you tell me those 2 cases?
1 and 2.
1 and 2, gracias. Perfect, perfect. Yes. So another example will be 22 equal to 3 times 7 plus 1. So whatever the remainder is, there is an inequality. The remainder cannot be anything you want to. The remainder from my college algebra class, or from 2nd grade also, the remainder, I'm going to call it R, is going to be trapped between 0 and the divisor. In this case, the divisor is 3. So, of course, when the remainder is 0, that means that you divide. 3 divides that number. So, anytime on a proof that I'm going to say, well, 3 does not divide B, I'm going to have 2 cases right there. If I need to hypothesize this, if this is a part of a hypothesis, I'm going to have case 1 when the remainder is 1. So whatever B is going to be equal to 3K plus 1. It's not going to be 3K. And then I'm going to have a case 2. Right there, where it's going to be B, it's equal to 3K plus 2, right there. So we can do a proof. We can do a proof right now. So here we were concentrating when we do not divide. So let's go and try to do a proof right now, right here. So if 3 divides x squared, comma, then 3 divides x, right there. That's an example where we're going to have cases right there. So here is the hypothesis. And here is the conclusion. Right there. And this is a true statement.
I have a question.
Yes. Go for it.
Are remainder equaling 0? Isn't that just not having a remainder? Why would
Okay, no, you do have, okay. You might think of not having a remainder, but the idea is when the remainder equals 0, that means that 3 divides that number. Let's go to the definition. You can do this. Can you see the definition that I have right here? Instead of writing B equals AK, I could potentially write B equals AK plus 0.
That makes sense.
My pleasure. Yes. Of course. So the remainder is 0 right there. I want for the remainder to be 0. I don't want to think I don't have a remainder. I want to think that the remainder is equal to 0 because we want to start playing with modular arithmetic. And one of the classes is going to be when you have 0 remainder. And those are all the multiples of 3 right there. Well, basically it's this. But thank you for the question. We will prove this. But exactly, perfect. Thank you for the question. When we do the divisibility by 3, So, or there on divisibility by 3, there we have the integers. And there we're splitting the integers into 3 pieces. All the multiples of 3. So all the integers that look like 3q. And those are the ones that have 0 remainder. And then all the integers that look like 3q plus 1. And all the integers that they look like 3q plus 2, right there. So we have those 3 classes. In this class, the remainder is 0, and I can denote it that way. The class of all the multiples of 3, and it is a 0 with those brackets. And then the remainder 1, and I get this infinite set that I'm going to give it that name. And then I had another infinite set that I'm going to call it that name right there. Here we're going to have all the multiples of 3. And so on. They are infinite. And then here I'm going to have all the multiples of 3 plus 1. Right there. I just need 3 negatives. Can somebody give me 1 negative for that class?
-4.
Let me check it. -4. I need to pass it. I need to check it. I need to do this equation. I need to solve this equation over the integers to make sure it works. Right there. So you need to get as an answer a q, that's an integer. So solve that equation. So can I put it in the second class?
No.
No, but I needed to check. But if it's not going to be in the second class, in which class is going to be? On the third one.
class.
Yeah. You got to be on that third class. That better work. Right there. If I try to solve that, it will work. Because, let me check. We'll get a -6. And it works. I can solve for q. Q integer. So perfect. The -4 is here. Right there. But then, of course, I'll put some positives. 5. 11. Right there. 23. 17. Let me write 17. Right there. 38. Look, the 4 that I just wrote in the third class, I think all of them are prime numbers. So the ones that are positive, they're all prime numbers, but that's not the case. They're not going to be always prime numbers. It's just like the density of the primes is so large as you start counting. But then I'm going to put here a 38, and that's it. That's over right there. So those were primes to begin with, and then that disappeared there. Yeah, 38. So perfect. Can you give me some negatives for the second class?
-5, -8, -11.
-5. Let's check. Yeah, that could potentially work, but I'm going to pass it through the equation police. Right there. So that is the equation police, and I definitely agree with you because it's going to be a -6. It's going to be a 3q. We'll be able to solve for q integer, namely -2. So yes. -5 is in the second class. And you can continue. They are infinite. There are infinite numbers on each class right there. So perfect. So these are the two cases that we need to play when you are not divisible by 3. Right there. So it's going to be a proof by cases. And of course, the proof by cases is just like the argument by cases. We have the argument by cases. So it's a legit method of proof. We're going to have cases. So perfect. So let's go back. Let's go back to that proof. If 3 divides x squared, comma, then 3 divides x, right there. Then 3 divides x. And this is for all x's in the integers. So let me write it as this is a universal conditional, but they wrote it briefly. Here it comes. For all x's in Z, comma, if 3 divides x squared, then 3 divides x, right there. There. So that's it. Those two are the same. Sometimes you don't write the universal on the front, right there. Perfect. And they could have said also let x be in Z, and that's acting like a for all. It's the same. It's a synonym. Right there. Let me write it. Oh, uppercase. Let, right there, instead of for all. Perfect. Okay, proof. Right there, proof. So, what am I going to do right now to be able to prove this statement?
Are you going to assume that 3 divides x squared?
I would have tried to do that, but then I will get nowhere. I will get nowhere because remember what we said, that algebraically, that expression looks more complicated than that expression, algebraically. And when the expression in the hypothesis, algebraically, looks more complicated than the expression in the conclusion, what do?
Take the contrapositive.
Take the contrapositive. So perfect. Yes. That's why we're going to have those two cases. But thank you. I would have started that way first. I would have started with the direct proof, but I would have hit a wall right there. And then I would have said, no. Look, let's try it. Suppose we would have not realized right there. We need the contrapositive. But suppose we say we don't realize. So we assume this because that's what I would have done right there. So I will say let assume x is in Z. Also assume that 3 divides x squared. So what am I going to say next?
Are you going to use the definition of division?
Yes. By definition, comma, x squared. It's equal to 3q. For some q in z. Right there, perfect. And then what am I going to do next?
Don't you just need to rearrange it so that it looks like the conclusion? Or now? Or
Yes. Bring, I want to write consider, and I'm going to bring that. I'm going to bring the x. Yes. And then try to rearrange it. Yes. Consider. X. Consider x. I brought it in. But now I need to just try to get x from here. Try to get x from there. And how can I get x from there?
You can take the square root of 3q.
Yes, square root. What happens when I square root both sides? I get a plus or minus square root. But in this time, I'm not going to get a plus or minus square root because what is this equal to?
Equals positive.
No. Oh, x positive. Yes. But can we say it better?
the absolute value of x, because x.
Perfecto. Yes. Well, now nothing makes sense right here. Nothing makes sense because look at q. Q is in z. Q is in z. Can q be negative?
Yes.
Yes. So nonsense. I'm getting nonsense out of this right there. And then of course I turn the x into a positive x. But this theorem is not about a positive x. It's for all x's in z. So can you see, if I try to go with the direct proof, I don't get anywhere right there. I just start writing nonsense right there. So who's my best friend?
Contrapositive.
The contrapositive. In this.
Recording in progress.
So perfect. So then prove by contrapositive. Prove by contrapositive. And I'll write the contrapositive. So right there, I'll write the contrapositive for all x's in z. Right there. And I'll let you write the contrapositive just to practice. And then I'll write it in 1 minute. I'll write it in 1 minute. There. I'm looking for another example. So this is, so we are going to need the test material for test 1, also for test 2, right here. We need the, not every topic, but a lot of it, because we need the contrapositive. There. Perfect. If 3 does not divide x, then 3 does not divide x squared. These statements are equivalent. So I can prove that one. I can prove that one. And that one will have 2 cases, because 3 does not divide x. You have the case with remainder 1, and you have the case with remainder 2. Right there. So let's go for it. Let's go for it. So right there, it now becomes a proof by cases. Right there. So assume, let x be in Z, comma, assume, well, let x be in Z, I'll put a period, assume three does not divide x. Assume the hypothesis. Right there. So case 1. Oh, I was going to write cake instead of case. I'm hungry. Yeah. Case 1. Right there. Let x be equal to 3q plus 1. Or 3k plus 1. Perfect. Right there. So that's case 1. Of course, for some k, in Z. Right there. Perfect. And then below, around here, I'm going to put the case 2. I'm going to start the case 2. Case 2. Let x be equal to 3k plus 2. I can use k again, but let me use L because we know that the cases are independent, and I can use k again, but let me use L just to play safe when I have other proofs to do, to make sure that I call them different right there. It doesn't matter for cases, but I want to play safe. L in Z right there. So let's go to case 1. What am I going to say next?
Three L plus 2. Oh,
3L plus.
why did you do 3k plus 1 and then 3?
Oh, I'm sorry. No. Yeah. I was thinking of cake. Yeah, perfect. Right there. Happiness with that. Happiness. Thank you for coming to the rescue. Thank you. You should eat. Yeah. I had my office hours full, so I couldn't eat, but I was doing a lot of curvature. Calc 3, yeah, tons of curvature. Right, so let me now, what am I going to say next in case 1?
Now can you square both sides?
Oh, of course. I'm going to bring
you have
x
to say
squared.
consider first.
Yes, consider x squared. Thank you. Yes, I have the expression that I need right there. I cannot assume all of it, but I need to bring that piece down. Perfect. Yes. Consider x squared. Consider x squared. Period. Let me write the consider a little bit better. And then, of course, I'll have to move the x squared there. No problem. Period. Right there. By algebra, by plugging an algebra, we get by plugging an algebra, comma, we get, and that's it, we have it, is x squared equal to 3k plus 1 squared. And that is the 9k squared plus 6k plus 1. Let me erase, and then I'll have case 2 again right there. Check me that I've done that correctly. I expanded, and I did a 3k plus 1 times a 3k plus 1. Perfect. And now look, we are going to factor a 3. Right there. So we're going to factor a 3. And look, that looks like a multiple of 3 plus 1. X squared looks like 3 times a multiple of 3 plus 1. Right there. You can make a u substitution. Make u equal to 3k squared plus 2k. But it is not divisible. X squared is not divisible by 3 because you have the remainder of 1 right there. But of course, we're going to say this. We know (3k squared plus 2k) is in Z right there. And let me write that a little bit better. We know (3k squared plus 2k is an element of Z by closure, because k is an element of Z by closure. Right there. The integers have closure and their addition and multiplication. Thus, 3 does not divide x squared. It's a clear remainder of 1. That you have a remainder of 1 right there. So 3 does not divide x squared. That was only case 1. We need to do case 2 right there. So let's go for case 2. Case 2. Right there, case 2 is going to say, let x be equal to 2L plus 1. 2L plus 2 for some L in Z. Right there. So we have the other case. Oh, 3. I'm sorry, 3. 3L plus 2, right there. We're talking about divisibility by 3. So that's not divisible. X is not divisible by 3. It has a remainder of 2. And those were the two cases. We have two cases on the remainder. The remainder could be 1 or the remainder could be 2 when you are not divisible by 3. Okay, with that, if the remainder is larger than 3, well, you can divide one more. Can you see? That's what they taught me in 2nd grade. Okay with that right there. So just checking right there. Yeah. So those are the two cases. So that's it. Let's go on. Consider x squared. Right there. So by definition, well, right there, by plugging an algebra, we get, or we can see, and that's it. X squared is equal to 3L plus 2 squared, which is equal to 9L squared plus 12L plus a 2 squared. Right there. I expanded. Check me on that. Check me on that because I'm hungry, so I can make typos. There. Okay. And then what we did before, factor. Right there. I'm going to factor. I'm going to do this. This case is more exciting. Can you see what I did? Yeah, the 4 needs to be turned into a 3 plus 1. And then I'm going to factor the 3 because I want to make it look like 3 times a little cloud plus a remainder. There. And now, same thing, talking about closure. See that? Oh, let me put something that one of my students wrote in 2011. She wrote, "It is evident." That sounds really cool. It is evident that 3L squared plus 4L plus 1, it's an element of Z. We know that is by closure, but then she decided to say that, and that's perfectly okay. It is evident. Let me fix a little bit there, the I and the T, perfect, and the D, there. Thus, it's clear that we can see a remainder of 1. So thus, comma, 3 does not divide x squared as desired. Oh, my pen is low, so I'll get my other pen. Perfect. So there. So perfect. As desired. There.
Quick question.
Yeah.
So for each case, we're not trying to make it so that x squared, for like case 2, we're not trying to make it so that x squared is equal to 3 times some integer plus 2. We're just trying to show that x squared is not divisible by 3, which is shown by 3 times some integer plus 1.
We need some remainder. Yeah.
Okay,
I don't care if it's remainder 2 or remainder 1. Can you make it equal to plus 2?
I didn't see a way.
No, of course not. Yeah, math doesn't have to give us excuse. Math is a language. And here I end up with a remainder of 1, and that suffices. But your question is pretty cool, because I would have thought the same thing. I would have thought, okay, because here we have x equals to 3k plus 1, we end up with a remainder of 1 on x squared. And on the next case, because we made x equals to 3l plus 2, I expected that it will end up with a remainder of 2. But whatever I expect, math also have, because it's a language math, you can expect the unexpected. Okay with that? Because that's part of being beautiful too. Expect the unexpected. Happiness?
Thank you.
My pleasure. My pleasure. Yes. Yes. Yeah, no, but I had the same issue. Going through the proof, I remember the first time doing this proof, this type of proof, where I had to use the contrapositor on divisibility, I expected that the remainders were going to match. And no, they didn't. Right, perfect. Okay, another example. This one, just to practice a proof, let x be in Z. So for all x's in Z, period, if 2 divides x squared minus 1, then four divides x squared minus 1, right there. So let's do that proof right there. Let's see. So we start like always. This one, I'm not going to use the contrapositive here. They look equally confusing, both the hypothesis and the conclusion. So no, not a big deal. This is going to be a direct proof. We're going to have this. That's the hypothesis. We are going to assume that, the orange, and we need to arrive to the green right there somehow. Perfect. So let's start. Proof. Assume two divides x squared minus 1. Right there. Oh, also I needed to say that sometimes they omit saying let x be in Z. Okay, we have to start the proof, or assume x is in Z. Sometimes I just did it. I took it as yeah. So sometimes you can get away with that right there. But let me write it. But of course, I cannot get away. I need to assume 2 divides x squared minus 1. I need to, that one I cannot omit. But let me erase it and also say let x be in Z to start right there. Assume x is in Z, but this one is optional, the one I'm writing right now. Sometimes I can omit it. Also assume.
I have a question about that.
Yes.
Is that, you're saying that we could choose to leave off the assume statement, not that they'll sometimes not have the let x be in Z statement?
Sometimes the let will not be there, because if you're what I'm saying right here is this. Sometimes I can write only this. That only. And sometimes I can write this. Right there. Both are okay. Both are okay right there. Happiness with that. Ansley, did I answer your question?
I think so. I think that I was confused because I thought that you were saying, oh, we're always going to be talking about integers because it's modular arithmetic, so they don't need to tell us as a part of our problem that x is an element of z.
Yes. But yeah. No, on this one is more confusing because you have x squared minus 1. But the one up here, the one that I started with, the problem that I started with right here, because you only have an x right there, and you are talking about divisibility, and it's not x squared minus 1, but it's only x. So somebody might say, you don't really need this portion right there because you are talking about divisibility. And if you are talking about divisibility, it's going to be over the integers. It's not going to be over 3.5 or over the reals. It's not going to be divisibility over the reals. It's divisibility over the integers. So I could get rid of that for all statement. Are you okay with that, Ansley?
Yes, that makes sense.
My pleasure. My pleasure. So can you see how much we're talking about math as a language in this class? Not so much that in Calc 2 when we're solving complicated integrals or Calc 1 where we're taking derivatives. Here constantly we're talking of math as a language. Okay, perfect. So here I'll erase the top one and I'll leave it like that. There, perfect. So then that's it. Oh, my voice is changing out of emotions. So we go for it. Yeah, this is really cool. So then of course we're going to use the definition. We're going to say by definition, we have by definition we have that x squared minus 1 is equal to 2k for some k in z. Right there. Happiness with that. Right there. So let me tell you what happens next. You are going to hit a wall. Sometimes math, like a language, doesn't have to ask you permission. And potentially it's going to be frustrating if you try to do anything else because I have a 4. So when I tried to do this proof for homework long time ago, I got stuck. I remember I didn't know how to continue. But let me tell you what to do. But it happened also maybe in Calculus 1 that you didn't know how to continue. Or it could happen in Calculus 2 that you get an integral that is the secant cube x dx, and it's an integration by parts. And there is no way that you see that being an integration by parts. Right there. So here, potentially, what to do next is this. By algebra, comma, we have There. Right there. Are you okay with that move? With that algebraic move? And now, what can you tell me about x squared?
Positive.
It's an odd number.
It's an odd number. It's 2k plus 1. X squared is odd right there. Okay with that? And that's going to help us. Because if x squared is odd, what is x?
Not an integer? No.
No, if x squared is odd, x is
Odd.
odd. We proved it in class. We proved it in class long time ago before test 1. If x squared is odd, then x is odd. So I will say this by a previous result. I'm going to say, see that x squared is odd. So we have that x squared must be odd, must be an odd integer. X squared can you see it has a remainder of 1 when you divide by 2. It has a remainder of 1 right there. So we have that x squared must be an odd integer. By a previous result, comma, x must also be odd. Let me write the statement right here, the previous result. If x squared, I'll write it like this. If 2 does not divide x squared, then 2 does not divide x. Right there. So that is to be odd. That is to be odd. 2 does not divide. You get a remainder of 1. See, x squared is odd. X is odd. Can you see that one looks similar to the one that we just did with 3? That we did that one just today. If 3 does not divide x squared, then 3 does not divide x. Well, it happens with 2 also. We did that one like 2 weeks ago. Okay, perfect. So I didn't need to write the previous result, but I put it right there. You don't need to prove it. You can need to call the previous result right there. Otherwise, the proof will be too long. So that's it. Thus, x is equal to 2l plus 1 for some L in Z. Right there. Perfect. Right there. So this one is a more complicated proof than the ones that we've done in the past. Now you're ready to bring that expression. Let me erase it and put it in orange. You are ready to bring that expression. Bring it in. Consider x squared minus 1 and plug in this latest information that we have. Consider x squared minus 1. So by algebra, by plugging an algebra, we get, and we run with it, is x squared minus 1 equal to 2L plus 1 squared minus 1. And now we continue. 4L squared plus 4L plus 1 minus 1. Right there. So check me on that. I expanded. Make sure that I expanded correctly. 2L plus 1 times 2L plus 1 is that. And then I'll drop the parentheses and cancel. Right there. I drop the parentheses and cancel. Oh, cancel. Right there. And then factor 4. Right there. So that's it. We just shown that 4 divides x squared minus 1. X squared minus 1 is 4 times something, right there. So the crucial moment in the proof was this. That to be able just to rewrite, okay, I'm sorry, not that, that's not the crucial moment. The crucial moment is upstairs, here, this one. I got stuck on that proof. We had that proof for homework. I got stuck on that proof, and my study group got stuck on the proof too, right there. And of course, still somebody would just try something in the study group right there, and then that's it. Somebody in the study group would try something. We were a study group of 4 at the library right there. Happiness with that. Yeah. I'll tell you the story. One time I was walking with my wife in the middle of nowhere in Switzerland, in the middle of nowhere near Wengen, and all of a sudden I hear Gustavo from a female voice. It was in the middle of nowhere. We were just me and my wife, and I hear a female voice, and I hear Gustavo. So I look at the sky thinking that was God. Okay, well, and it wasn't. It was Eva Togores from my study group. Right there. She was the basketball player in the group right there. Perfect. Yeah. I remember that she will say hi to me by punching me in the stomach right there. She thought everybody had her abs. No, I was like that. Yeah. Okay, small world right there. Because if you find somebody at HEB, it's not a big deal. But in the middle of Switzerland, that was, yeah, perfect. She was there with her partner. Perfect. That's it. So now that I'm going to talk about closure right there. So right there we go. So there, L squared plus L. Well, we'll say that it is evident.
Professor, do you have enough time to answer a question?
Yeah, of course. Let me see. Let me check the time. I haven't been checking the time, but let me move it right there. Let me move some things around. There. 7:12. Yeah, let me finish the proof and I'll answer your question, Anthony. Pleasure.
Okay.
Yeah, it is evident that L squared plus L is an element of Z by closure. Thus, 4 divides x squared minus 1 as desired. there, and I'll put a little box right there, and there we are done. So perfect. Look at the formal proofs. You need to start grabbing your sentences, or just copy my sentences, but just start finding your style in writing your proof. It's just like you find your style when you're coding. When you're coding, you find your style and you make your comments. This is very similar. So Ansley, what's the question? Pleasure to answer the question.
I was following until you said that 2 can't divide an odd number and 4 can't divide an odd number. So after we determined that it's an odd number, I thought that we were done. And I was confused why we kept going, what you were doing in the second consider.
Let me check. No. The issue is this, Ansley. I'm saying that x squared is an odd number. X squared is an odd number. I'm never saying that 4 cannot divide, because look, on this proof, it was x squared being an odd number. And what is x squared minus 1?
Oh, it's an even number.
It's an even number, but I'm not sure if it's divisible by 4, because you are divisible by 2, of course, but you are not necessarily divisible by 4 if you are even. And that's what we prove. So nowhere here we use the contrapositive. Yeah, go ahead, Ansley.
No, that makes sense. I understand now.
My pleasure. Yes. So that was a medium to spicy, but somewhere between medium and spicy level, that the proof that we just done. You have to assess the difficulty right there. So you're not going to have a test 2 that has all the proofs at this level. That will be insane. So you have maybe 1 proof at this level, and other proofs that are going to be simpler than this one. Okay with that? Okay. And of course, you might have one conditional statement that is not true, but I will tell you it's not true. So I will tell you, show that this statement is not true. So you use a counterexample. So here I'll tell you, show. Let's say P implies Q is false. So then you use a counterexample. So it will be proved by counterexample to show falsehood of a conditional statement by counterexample. Right there. For the test, I'm sorry, I was reading a book in Spanish about the names and the nights. I was reading a book in Spanish. So then I saw the puzzle. I saw the puzzle right there in Spanish, right there. So I translated to English and I put it on the test. But I switched two of the situations in the puzzle, and the puzzle had no solution. So to all of you, I'm going to give you full credit for that problem. Okay, with that, I am very, very sorry. So all of you get full credit. I never meant to put a problem that didn't have a solution. So the solution to the puzzle was no solution, and it was my fault. So you get there a full credit for that problem. And of course, in Spanish, the knights are, a knight is a caballero or a dama. Caballero, or the feminine would be dama. And the names, the name, it's a granuja in Spain, in Argentina too, granuja. But in Argentina, we also can use ciruja. Right. Which is a little bit of an insult. It's an insult. If I call somebody a granuja, they might just smile because they're my friend. but they might just also hurt me right there. The different level. Yeah. Okay, yeah. So perfect. So I'm sorry. I was translating right there. So those are synonyms. So okay. So all the proofs will be true statements right there, and I will double check, of course. And then there will be one that will be a false statement, and I will tell you, and you'll use a counter example. Happiness with that. Perfect. So the next thing that we're going to see next class is the quotient remainder theorem. We cannot prove it because we need induction. We need a new method of proof that we are not going to be able to see till like 2 weeks from now. Quotient remainder theorem. There. And of course, is this idea that A, when you're trying to divide B divided by A, or vice versa, A divided by B, A is going to be equal to BQ plus R, right there. So you have the existence of these two elements there. And of course, I'll put the theorem in full splendor next class. And here's going to be the remainder. It's going to be trapped between, B, Q are the existence of those unique elements, the divisor. So B is let me call it D for divisor. That makes more sense. D, DQ plus R. A is going to be equal to DQ plus R, and the remainder has to be less than the divisor. So we'll see that next class, right there, and we'll use the Euclidean algorithm. After this, we'll see the Euclidean algorithm. We'll see one algorithm in this class, right there. Our first algorithm, right there. So super ultra freedom. Any questions? And if you have a question, you can stay.
Dude, I've been to Hooters in so long.
Wait, they're out of business?
Yeah, they're shutting down.
I mean,
nobody wants to leave to go see tits. They just see it on the internet, like,
yeah,
and they can order in with DoorDash and
there's
then
no more
watch
Gooners.
porn.
There's no more. Yeah, there's no more Gooners going to Hooters. They're all in Pika Stream.
Yep. What?
All the Gooners aren't in my stream. I mean, Hooters is expensive. I mean, the place
Dude,
taxed.
you are literally putting Hooters out of business.
No, it's not. It is actually not me at all.
All right, so Wilds, ever since I've had a podcast, which was 2007, Wilds will come on and do half-baked ideas. And I don't remember the first time he did it, but many of them are on YouTube from 08, 09, 2010. Then on this pod, when we brought it to the Ringer, same thing, he's popped on. Now he's a busier guy. But every once in a while, we have to grab him for the half-bakes.